Okay, any questions about anything? All right, as everybody knows, there's no class next Monday or Tuesday. So I'll see you after today. I'll see you next Thursday. And 3 weeks from today, I think it is, Friday or Thursday, March 12th at night, we have our first prelim. And so haven't decided quite what that's going to cover yet. It's a little late in the semester for a prelim 1, but it was the only date we could get because of all the scheduling issues. So anyway, you'll know, I'll let you know what homeworks it covers, what lecture material it covers, and all that stuff. But anyway. And also, there's one other thing that came up this week. When the TAs posted the grades for homework 1, apparently the comments didn't post. Did anyone, was anyone successful in reading a comment about his or her homework? Or no? Did you even look? I know at least one person looked because they drew our attention to it. Okay, so if that happened, I and some of the TAs figured out how to put up comments and save them. So what I'd like to say now is, sorry that happened on the first homework. I think it's kind of unsalvageable, but henceforth you will be getting comments that you can read. Okay, so that's what we're going to do. Okay, so anyway, last time the main event was this Shannon Nyquist sampling theorem. And it goes like this. If you have a signal x of t that's band limited, and I told you that when we're talking about signals that are just sums of sinusoids, that just means that the max term frequency, the max frequency of all the terms, is finite, and that the bandwidth is f max. So that would be the bandwidth of a sum of sinusoids. It would be the frequency of the maximum frequency term. And f sub s is bigger than 2f max. Then you can, in principle, recover x of t from the sampled record x of n equals x of nts, where ts is equal to 1 over fs. And pictorially, this says that if you take x of t and you put it through an ideal C to D with sampling frequency fs, and sometimes we're going to write fs, sometimes we're going to write ts, it's the same thing, and you get x of n out of that, you can put it through something that I called a magic box. And today we're going to talk about what's inside the magic box, at least briefly. And this is going to be what's called an ideal D to C with interpolation interval Ts. And what's going to come out of that is x of t. And the in-principle reconstruction is what's happening inside this magic box. And more generally, if x of t is a linear combo of, well, let's say it for one sinusoid. So more generally, if x of t is just any pure sinusoid, then, and no matter what fs is, we have this. That if you take x of t and you put it through that ideal C to D with sampling frequency fs and get x of n out of it and put that through the magic box, what comes out of here is going to be the principal continuous time alias of x of t with respect to fs. So x print of t. So that's the principal continuous time alias of x of t with respect to fs. So even if the conditions of the theorem aren't satisfied, we know how this sampling and interpolation system operates, at least on pure sinusoids. And extending it by linearity, it turns out that the ideal C to D and the magic box are both linear. So by linearity, it turns out this last thing applies to any, so if x of t is any sum, any finite sum of pure sinusoids, then this picture, the output x of t goes into this thing, C to D, TS, or FS. X of n comes out of here. And the magic box puts out the sum of all the principal continuous time aliases of the individual terms with respect to Fs. So sum of the individual terms. Principal continuous time aliases with respect to Fs. All right. So that's what's going on so far with this. Now, what I want to do today is, first of all, I want to talk about a situation where this second board occurs, in a sense that you don't have the conditions of the sampling theorem satisfied. And before I do that, I want to tell you a couple of pieces of terminology that you'll hear on the street. Okay? So here's some terminology. First off, if x of s, or x of t, I should say, is band limited and bandwidth of x of t, which is like the max frequency of x of t, is f max, we call the frequency 2f max, we call that number the Nyquist rate for x of t. Or the Nyquist rate of x of t, or x of t's Nyquist rate. So the colloquial way of talking about the sampling theorem is that if you sample a band-limited signal faster than its Nyquist rate, you can recover the signal from the samples. So theorem says, if you sample a band-limited x of t faster than its Nyquist rate, then you can recover x of t from the samples in principle. OK, so that's something that people talk about. Sampling faster than the Nyquist rate. And sometimes I'll say that. I'll say you sample x of t faster than this Nyquist rate, or you sample x of t Nyquist fast enough. You know, that, you know what I mean when I'll say stuff like that. OK. All right, so what if you don't sample a signal faster than its Nyquist rate? Or what if the signal isn't even band limited? OK. So if the conditions of the theorem don't hold, if they fail, for example, if x of t is band limited with bandwidth f sub max, and your f sub s is not bigger than the Nyquist rate. So f sub s is less than or equal to 2f max. Then we say, and there's lots of ways of phrasing this, but let me just give you a few common things. We say, quote unquote, aliasing occurs, or quote unquote, the samples in x of n, which is equal to x of nts, are aliased. That's another thing that people say. That's the kind of talk that people give around the situation where you're not sampling a signal faster than its Nyquist rate. And they also say that when x of t is not even band limited, so it doesn't even have a Nyquist rate. But anyway, aliasing. And one of the kind of background ambient mantras of signal processing is, quote unquote, aliasing is bad, right? You want to avoid it, okay? So this is sort of an overarching, and I want to say truism, because in a sense, you know, like we know what happens when you sample slower than the Nyquist rate. So it's not like we don't know what happens, but in applications, we generally want to avoid it for various reasons. And I'll draw a picture that I hope illustrates that a bit. So the overarching truism of signal processing is that you want to avoid it. We want to avoid aliasing. We want to avoid sampling signals in such a way that the samples are aliased or that aliasing occurs. And so what you'll see in applications, and this is just a really general picture, you see systems, signal processing systems, so SIGPROS systems that look like this. You have a continuous time signal, x of t, so this is continuous time. And first you put that through what's called an anti-aliasing filter. Have you ever heard that expression in life on a project team? I don't know. How many people are on project teams? Yeah.
You. Like in Photoshop.
Photoshop. OK, cool. That's a good project team kind of thing.
No.
No.
It's not. Well, I'm on a project team, but not for.
You know, I got to admit something. I've never learned Photoshop. I don't know how to do it. It's OK. OK. All right. So we put this through what's called an anti-aliasing filter, whatever that means. It's going to be essentially a low-pass filter that chops off any frequency content outside of a certain bound. And we do that because then we're going to put it through a C to D with Fs. And this signal here is going to have bandwidth F max less than Fs over 2. So the anti-aliasing filter sort of artificially adjusts the input signal so the sampling will be Nyquist fast enough. Then you put this guy, let's call this Q of t, and so we get Q of n out of here. We put this through a DSP kind of system, like a discrete time system. And we're going to be talking about those after we're done with this discussion, like FIR filter or whatever. And what comes out of that is going to be some R of n, say. And then we put this R of n through a D to C with interpolation T sub s, and you get Y of t. So this is what DSP systems look like in real life, that you precede them with an anti-aliasing filter before you do all your signal processing. And one place where this comes up is like in the landline phones, which I still have my landline phone. I still pay ridiculous amounts of money for it. I don't know why I have this, because no one real calls me on it. But in the landline phone system, it turns out that the sampling in the DSP, the sampling, the C to D, occurs at 8 kilohertz. Okay, so why does that make sense? Well, speech, unless you have a really, almost dog whistle high voice, is all the action in speech occurs around, between up to, say 5,000 hertz. So, but the thing is, the signal going into the phone is not just speech, it's whatever else is going on. And so there's an anti-aliasing filter before the sampling occurs, and that's going to have what's called a cutoff frequency of 3 kilohertz. So filter makes the bandwidth of this guy 3 kilohertz. Sampling is at 8 kilohertz. 8, is 8 bigger than 2 times 3? Yes. So yeah, so we have this anti-aliasing filter has set things up so that no aliasing occurs during the sampling. And then you have PCM and all that and whatever. So that's an example where that comes up. All righty. Now, I want to turn our attention back to the movie example to see what's going on there, to get a new slant on that, at least in one of the cases. And that's going to lead to yet another one of these cognitive science conundrums, actually is the plural of conundrum because it's not a Latin word, it's a made-up English word. But anyway, that have always bothered me or fascinated me. So let's see if they bother you and fascinate you equally. All right, so let's revisit the movie example, and specifically that second case, what we called case 2. Now, case 2, what was case 2? Case 2 was that the wheel, and I hope you guys were here for the movie example. If you weren't here, there's a video. You can watch it, not during class, but whatever. A wheel is rotating 18 revs per second clockwise, and it's filmed at 24 frames per second. Okay, so this corresponds to the case where, in a sense, what's going to be happening is f0, the frequency of the sinusoids of interest, is going to be 18 hertz, and fs, the sampling frequency, is going to be 24 hertz. And 24 is not bigger than 2 times 18. It's not bigger than the Nyquist rate. So aliasing occurs. All right, so let's look at this more precisely. Really what's going on when you're looking at the rotating wheel is you're looking at 2 real-valued signals, 2 sinusoids. You're looking at the x coordinate of the end of the radial marking and the y coordinate of the end of the radial marking. So watching wheel rotate entails watching the x of t coordinate and the y of t coordinate of the end, the outer end of the radial marking. Remember, we had the radial marking on the wheel so that our eyes could at least track what's going on. Now, in the case of the wheel rotating clockwise 18 revs per second, what are the x and the y coordinates? So here, in this example, what is the x coordinate going to be? Well, what is the x coordinate? It starts at 0, right? Because the wheel's up here. So let me put the wheel down here. And so on. This is just to jog your memory, so that's why I'm putting it in the liminal part of the board. Okay, that just sort of, in this example, the x coordinate starts at 0, right? And in real life, this thing is rotating clockwise, so it increases up to 1, and then down to 0, increases, decreases to -1, back to 0, up to 1. So it's following a sine function. So x of t is going to equal, say, r, where r is the radius of the wheel, times sine of 2 pi times 18t. So it's an 18 hertz sine wave. And writing that as a cosine, as we are wont to do, gives us r cosine 2 pi 18t minus pi over 2. And y of t, what does y of t do? Y of t starts at 1, goes down to 0, goes down to -1, goes back up to 0, goes up to 1. So y of t is just following a cosine. Y of t is equal to r cosine 2 pi 18t. And r here is the radius of the wheel. All righty, so x of t and y of t are both band limited. What is f max? Of x of t and f max of y of t? What is the bandwidth of each of those guys? Yes. 18 hertz, exactly. So what's your name? Nick? OK. I've asked you that before, right? Yes. And are you over the flu and everything?
I am finally over the flu and pneumonia.
Killer. OK, yeah.
It's been a while.
It was weird. You know, when I was in grad school once, I never get fevers. But all of a sudden, I had this like low-grade fever. And I didn't have any respiratory symptoms or whatever. And so I went to the health services. And they said, well, we're going to do a chest X-ray. I'm like, why? Well, just let us. And so they did. And they said, oh, you have walking pneumonia. I never would have guessed. You know, it was weird. But anyway, I know, TMI, right? OK, so each of these guys, both x of t and y of t, have f max equal to 18. All right. Meanwhile, fs equals 24. And this does not satisfy that fs over 2, that f max is less than fs over 2. So aliasing occurs. Because f max is bigger than or equal to fs over 2. All right. So let's see what would happen if we took the movie and we put it through an ideal D to C. OK, so what happens if we do this sampling? We do this. So we take x of t, and we put it through the, say, the C to D with sampling frequency 24 hertz. We get x of n, and we put it through the magic box with interpolation interval 1/24. Something's going to come out. Let's call that, say, q1 of t. And y of t, same thing. This is the movie strobing at 24 hertz. Y of n comes out, and the D to C, and call the output of that q2 of t. What are q1 of t and q2 of t? Well, we know that q1 of t and q2 of t are going to be x prin of t and y prin of t, the principal continuous time aliases of x of t and y of t with respect to the sampling frequency fs. So this is going to be x prin of t with respect to fs equals 24. This is going to be y prin of t with respect to fs equals 24. So now our job is to find x prin and y prin, the principal continuous time aliases. So what do? How does one find a principal continuous time alias? What's that?
Subtract 12 out of the frequencies of both of them, and we get 6 in both.
Yeah, that's true, but let's do it slowly. OK, you're right. To find these, what we do is we look at the frequency. We draw a frequency line like so, and we mark off what f0 is. So f0 is going to be 18 hertz, say, 18 hertz. That's f0. And then we step it, and here's going to be 12. That's fs over 2, and minus fs over 2. We step it down by integer multiples of fs until we land in the open interval minus fs over 2 to fs over 2. And here, obviously, the pesky boundary case does not apply. That applies in the case when it's going 12 revs per second to the right. So we go down like so, and boom, we land at minus 6. All right? So this is one thing that can happen when you're figuring out principal continuous time aliases. And what it does is it results in a 6 hertz cosine with a phase reversal. So here we have, these are our two cosines. This one, 6 hertz cosine with a phase reversal, there's no phase, so it doesn't matter, or 0 phase, it doesn't matter. This one turns that into a plus pi over 2. So now we get x prin of t equals r cosine of 2 pi times 6t plus pi over 2. And y prin of t is equal to r cosine 2 pi times 6t. Now, what do those x and y things correspond to in terms of real-world rotation? Well, cosine shifted to the left by pi over 2 is minus sine. So this is the same as minus r sine 2 pi times 6t for our new x at t coordinate. And if you look at what these guys are doing, all right, what is x doing? X is starting at 0, and then it's going negative. And then it comes back up to 0, and then it goes positive. So this is that. This guy is doing the same thing as it was before. It starts at 1, goes down to 0, comes back up, and so on. So this corresponds to counterclockwise rotation 6 revs per second. Yeah.
Why didn't you reverse the phase on the y?
I did. The phase on the y is 0, and minus 0 is 0.
Oh, okay, I get it now.
Got it?
I thought you'd be like subtract or add.
No. Yeah. I've noticed in some of the Piazza comments there's a little bit of confusion about negative f versus negative phase. You'll get used to it, after you do a few problems. So when you have 0 phase and you reverse that phase, it just becomes 0 again.
Yeah.
All right. So bottom line, if you were to take this movie, if you were to take the x and the y coordinates that you get from filming the movie and put them through an ideal D to C, the signals that would come out, these principal continuous time aliases, are the x and y coordinates correspond to counterclockwise rotation at 6 revs per second. Now, what is surprising to me about this from a cognitive science standpoint? This is a math thing. You're putting a sampled x of t and y of t through systems, and something's coming out. But when you watch the movie, that's a brain thing, right? You watch the movie, and that's what you see. Okay, so in a sense, upshot of this is that because this is like what we see, so because this is what we think we're seeing, this is the way our brain puts it all back together, our brain, and when I say, well, let's say your brain, and when I'm putting brain in quotes because what I mean here is the whole visual apparatus, starting with the retina, the optic nerves, the visual cortex, and all that stuff, and whatever cognitive machinery you happen to lug along with you, puts this back together just as the ideal, the magic box would, / ideal D to C. Now, why should it do that even? Why shouldn't it put it back some other way? What do brains do? Brains find, we talked about the cave people. The Darwin Award-winning cave people came up with complicated explanations, and the ones that survived came up with simple explanations. But wait. Brains are supposed to come up with, quote unquote, simplest explanations for what they see, at least if they are going to survive to give rise to future brains. Here we see, the brain comes up with what we might call the quote unquote lowest frequency explanation for what it sees. Why is simple the same as lowest frequency? That I don't know. Okay, why should simplicity correspond to lowest frequency. Again, we have this mysterious cognitive importance of this frequency concept. Remember, like I was saying earlier, like why do we feel compelled to divide up the world of signals in terms of frequency? Is it because of the math? Or is it because the way our cochleas are put together that are spectrum analyzers? Here, there's yet another kind of thing. Low frequency corresponds to parsimonious or simple explanation. Okay? And let me tell you that word, parsimony. Has anyone seen this word in a science course, like a parsimonious explanation for something? Like what science course did you see it in?
So I'm a bio major.
Yeah.
And for phylogenetic trees, when we're making like those trees, the most parsimonious tree is basically the one that includes like the least mutations on like basically
Right.
makes it less complicated.
Yeah, it's the one, it's the one that Occam's razor left behind, so to speak. Okay, so parsimony is simplicity in science. So brains come up with parsimonious explanations, they come up with simple trees, they come up with low frequency signals. But why is low frequency the same as efficiency or parsimony? I don't know. Okay, fascinating concept to me. Okay, so that's an unanswered question. So I'll put 2 question marks by that. All right, so that's the revisit of the movie example. Any questions about that? Yeah.
Excluding from this, as if we were trying to watch it spin forward at 18 reps per second, we would think we were seeing it spin backwards at 6 reps per second. Is that what this finding shows?
Well, I claimed that before when we talked about the wheel, where you might not have been here that day. Oh, watch lecture 8. Yeah, actually, I sent my brother the link to that lecture because, and at 22 minutes is when I bring up the Modern Farmer TV show, which totally did exist. But anyway, it's his birthday today, so I have to, happy birthday. If he ever watches this video, if I were him, I wouldn't sit around watching me on video. No, I told him at 22 minutes, if you go to 22 minutes in lecture 8, that's when I talk about the wheel. And in the movie, when you strobe the wheel 24 frames per second and it's rotating 18 reps per second clockwise, you see the radial marking, it quote unquote looks like it's going left. And so that's how, like when you watch a car commercial, the wheels on the car, like do weird things, Anyway, that's, yeah. Okay. Any other questions about this tying the movie example back to the principal continuous time aliases and so on? All right. Let me tell you a little bit about what's inside the magic box. Why not? So what's inside the magic box? Namely the ideal D to C converter with interpolation interval T sub S. That's the name. That's the official name of the magic box. All right, the magic box is an interpolator. We have talked about interpolators before a little bit. Okay. It's an interpolator. It's an interpolator, just as these 2 other ones we talked about earlier, the so-called zero-order hold interpolator, the one that generates a step function, and the linear interpolator, the one that connects the dots, those are interpolators. So just like the zero-order hold and linear interpolators that we visited before, what does an interpolator do? it takes the input signal, a discrete time signal, say x of n, and it puts out, so this is going to be our d to c with ts as the interpolation interval. It puts out a signal, continuous time signal y of t, where y of n ts equals x of n. In other words, y of t interpolates x of n. Now, the ideal d to c does this in a really special way. Okay? Now, it turns out that all the kind of systematic interpolators that people build out there, and there's plenty of them. You know, there's things like there's a linear, there's a zero order hold, there's, you know, cubic splines, whatever. You know, a lot of it is about curve fitting, and they come up in all kinds of applications. But they take a special form. So most interpolators, most sort of cool real-world interpolators arise as follows. That your y of t is going to be the sum from n equals minus infinity to infinity x of n times something I'm going to call g of t minus nts, where g of t is what we call an interpolation function. And what properties does an interpolation function have to have? It has to satisfy the following. We need, first off, that g of 0 equals 1. And second of all, that g of any integer multiple of ts other than 0 is 0. And the reason we need these things, if you look at that sum, you'll see, well, what if I plug in nts for little t? I want to get x of n back. And that means all the other terms except the one involving x of n have to be 0, blah, blah, blah. So anyway, I don't want to get too deeply into this. This is a topic for another course, or EC 3250 or whatever. All right, for the zero order hold interpolator, the one that puts out a step function, we have, this is our g of t. G of t is going to be 1 at 0, and it's going to stay 1 out to ts, and then it's going to be 0 for t bigger than ts, and 0 for t less than 0. So this is our g of t. That turns out to be the interpolation function for the zero order hold interpolator, the one that puts out a step function whose staircase values are the x of n's. For the linear interpolator, it turns out, and maybe I'll give you a homework problem on this. This might be good. Although the book probably does it, so. I forget whether the book does it. That was definitely my phone. So for the linear, the connect the dots interpolator, it turns out that this is what g of t, interpolator, this is what g of t looks like. It looks like this. And this is not obvious at all to me that it does, but this is what it looks like. And it's 0 outside of there. And this value is 1. All right. So what is the interpolation function g of t for the magic box? So for the magic box, it turns out that, does anyone know what it is? turns out that g of t equals sine of pi over ts times t divided by pi over ts times t, a sinc function. We've seen sinc functions briefly before, but let me graph it for you. And this is why some people call the magic box, the ideal D to C, a sinc function interpolator with interpolation interval Ts. So let's look carefully at this. That's not bad, actually, if I do say so myself. Yeah, let's take the 3-minute break, and then we'll put labels on this graph and continue on from there. And I can see who's texting me. Are we back live? All right. So this is a special function. This is a really cool function, and it's called a sinc function. Let's put some labels on the graph. What is the peak here? The peak at t equals 0. Have a look at the formula here. What do you see? You see at t equals 0, it looks like I'm dividing by 0, right? But this is of the form sine theta over theta as theta goes to 0. And everybody knows, right, sine theta over theta goes to 1 as theta goes to 0. So this peak value here is 1. And you can find that any way you want. You can find it just by memorizing that sine theta over theta goes to 0. Or you can do L'Hopital or whatever. And I'm going to turn the sound off on my phone because clearly some people are having a conversation that they want me to be involved in. And so, all right. So that's 1. Now what are the 0 crossings going to be? The 0 crossings are going to be when sine pi over ts times t is equal to 0. So the 0 crossings are when pi over ts times t is equal to some integer multiple of pi. So the first 0 crossing is going to be when this is equal to pi, and that's the same as t equals ts. So first 0 crossing is going to be at ts. And similarly, you can show that the second 0 crossing is at 2ts, 3ts, 4ts, and so on. N minus ts, minus 2ts, and so on. So this is a sinc function. Note that the sinc function satisfies these two requirements that apply to any interpolation function g. Namely, that it has to be 1 at t equals 0, and it has to be 0 at all the integer multiples of ts other than 0. So it is a valid interpolation function, and as it happens, this is the interpolation function for the magic box. So sometimes I'll refer to this as an ideal D to C with interpolation interval Ts. Sometimes I'll refer to it as a sinc function interpolator. You know, none of these differences should bother you. I hope they don't. So thus, so we often refer to the ideal D to C with Ts as a quote-unquote sinc function. And by the way, I have no clue where the name sinc comes from. Does anyone know? Do you know? Alex? No? Why didn't we ever look that up? When we learned about it. He might have an idea. So what's
the cardinal sign function? It's like
cardinal sign?
yeah.
This is a first. I have asked so many classes. Do you guys know where sinc comes? I haven't even. So cardinal sign. So where does that come from?
Honestly, I have no clue.
So it might have to do with cardinality or.
Yeah.
Oh my gosh. Well, I have to a sinc function T sub s interpolator. All right, so that's a perfect cardinal sign function. Wow. Maybe because it looks like a cardinal hat, like Catholic Church, kind of. You know, cardinals have hats that go, oh, or do only popes? I don't even know. I'm sorry. Yeah. Okay. All right, so this is all very cool. Anyway, so another route to this whole sampling and you know, interpolation stuff. But are we, by the way, the person who was asking about the magnitude? Nudge. Did you get this? Did you understand this after pondering it for a couple minutes?
I feel like I should understand it, but I don't.
Yeah, okay. This is worth talking just for a sec. You know, she was asking during the break, I have these AKs, right? And I want to draw the spectrum of the signal. And I have its AKs. How do I draw the, and the AKs are ugly. They're not like, you know, 5 e to the j pi over 3. They're like e to the j theta over 1 plus jk 4 pi. How do I even draw the stems? You know, what do I put the labels on the stems? I said, oh, just put that as the label on the stems, but get the lengths right. What are the lengths of the stems? The lengths of the stems are the magnitudes of the AKs. And when AK is presented as positive number times e to the j theta, that's easy. But when AK is presented this way, what is the magnitude? Well, the way to figure out the magnitude of a complex number, that is the ratio of two complex numbers, is that it's the ratio of the magnitude of those two, right? So numerator here is e to the j theta. That always has magnitude 1. Denominator is 1 plus jk 4 pi. That's presented to you in a nice rectangular form. So the magnitude of that is square root of the sum of the squares of the real. Yeah?
I guess I'm just confused why you have 4 pi squared instead of 4 squared pi squared p squared. Because it's supposed
Oh, I meant jk 2 pi. Sorry. Yeah, there we go. Thanks. OK. Anyway, so I can erase that. Another way of getting at a lot of this stuff having to do with sampling is, and by means of discrete time sinusoids and their spectra. And so that's what we're going to turn our attention to. This is going to be the last thing we're going to talk about for chapter 4 before we move on to the FIR systems. So this is sort of another path through the woods toward this, or the sampling / interpolation results, leads through these things called discrete time sinusoids and their spectra. And here, this is where, in my opinion, the book gets a little bit confusing because they use the words alias and all that in a slightly different way, and they don't draw, in my opinion, I'm always saying in my opinion because you might love it the way they do it, they don't draw attention to the important distinctions between what we've already done in continuous time and what we're doing in discrete time. All right, so what do I mean by a discrete time sinusoid? A general such thing is x of n is equal to a cosine n omega 0 hat, okay, awkward, but plus phi. That's the general form of a discrete time sinusoid. And what is A, the amplitude? A is the amplitude, obviously. That's what we, and omega 0 hat is what we call the normalized frequency. And some people like to say normalized angular frequency. And phi is the phase. And what we assume here is that omega 0 hat is positive. A is positive, and phi is in the interval minus pi, 2 pi, as usual. All right. Now, this definition, so to speak, of a discrete time sinusoid just sort of takes a continuous time sinusoid and just plugs in a discrete time variable in some sense where the continuous time variable is. But, and so you might think, OK, this must have come from sampling a continuous time sinusoid. But that's not necessarily the case. Sometimes you just stumble on a discrete time sinusoid. You don't generate it by sampling a continuous time sinusoid. So let me just note, okay, that x of n need not come from sampling some original continuous time sinusoid, although it might. It's a thing unto itself. It has an essence, whatever you want to say, no matter where you find it. So, you know, you don't, if someone comes up to you in Whole Plaza with a continuous, with a discrete time sinusoid of this form, you don't go and ask them, okay, what continuous time sinusoid did you sample to get that? Because for all you know, they found it under a rock or on live slope, right? We even used that analogy last time, right? Yeah. You can find a discrete time sinusoid out there in the world without ever dealing with a continuous time sinusoid beforehand. But anyway, okay. What about this normalized frequency omega 0 hat? It's positive. What dimensions does it have? It has no dimensions. Okay, so here's our first contrast with continuous time. So here's our first contrast with continuous time. So over here we have continuous time universe. We have a cos 2 pi f0t plus phi. Over here in the discrete time universe, we have a cos n omega 0 hat plus phi. F0 here has dimensions 1 over time. And it has units hertz. Over here, everything inside here is dimensionless. So omega 0 hat does not have units of anything, unless you want to call it radians. You know, radians is one way of, no, radians has dimension 1 over time, so it's not radians. No, that's, forget it. Anyway, that's what I want to leave you with. That continuous time, you have frequency that has dimensions of 1 over time. And in discrete time, you have normalized frequency, which is dimensionless. And that's one of the reasons people call it normalized frequency. All right, so the next thing, leading to another contrast with continuous time, is observe that for any integer k, and for now I'm just going to let k be bigger than 0, that if I change omega 0 hat by an integer multiple k times 2 pi, so a cosine 2 pi, or sorry, a cosine n parentheses omega 0 hat plus 2 pi k plus phi, that equals a cosine n omega 0 hat plus phi plus 2 pi k. And when you shift a cosine by an integer multiple of 2 pi, it doesn't change the signal. So you have a cosine n omega 0 hat plus phi. So this signal, this discrete time signal, is the same as this discrete time signal. These guys are the same discrete time signal. And remember, we called that x of n to start with. The same discrete time signal written in 2 different ways. Okay, so we can just think of these as different spellings of the same signal, different, I don't know what to call them. Okay, it's like, so there's the left signal is just a quote-unquote respelling of x of n. Okay? Now, what the book does that I think is confusing is they say this is an alias of this. This is an alias of that. That these are aliases. Now, why I find that confusing is that in continuous time, the aliases of a continuous time sinusoid with respect to a given sampling frequency are all different signals. Whereas in discrete time, what the book calls the aliases of the discrete time sinusoid with frequency omega 0 hat are all the same signal. Okay, so here's the second contrast. So here's some terminology. And this is common terminology. People call these different spellings I'll put that phrase in quotes. I think that's a decent analogy to what's going on here. We call these different spellings of x of n aliases of x of n. But this is sort of dangerous. It's somewhat misleading terminology because why? Because, again, let's do continuous time world. Continuous time that all the continuous time aliases of the signal x of t equals a cos 2 pi f0 t plus phi with respect to some sampling rate, say f sub s, are different continuous time signals. And why they are aliases of each other is because if you sample any of them at f sub s, you get the same discrete time signal out. In discrete time, all these different aliases, so-called aliases, are all the same signal. They are just different spellings of the same signal. So all these aliases of, say, x of n equals a cos n omega 0 hat plus phi are different spellings, are the same signal. Spelled differently. Okay, so that to me is a point of confusion in the book. Okay, now what do we do when we came upon the concept of aliases with respect to a sampling frequency in continuous time? We said, well, there are going to be aliases with arbitrarily high frequencies, but there's going to be unique alias of lowest frequency, blah, blah, blah. We can do a similar deal with all these different spellings of the same signal, the same discrete time cosine. And the drill works a lot like the drill in continuous time, except instead of shifting f by integer multiples of f sub s, we're shifting omega hat by integer multiples of 2 pi. So how's this going to work? All right, so given a discrete time sinusoid x of n equals a cos n omega 0 hat plus phi, there is a unique provided, so assuming, and this should be a lowercase, so I put a comma here, assuming that omega 0 hat is not an odd integer multiple of pi, and that's the pesky boundary case in this context. And Nick, because you missed the lecture on the movie, you missed when we learned about the pesky boundary case, so that. All right, so if omega 0 hat is not an odd integer multiple of pi, there exists a unique alias of x of n, that is to say, i.e. different spelling of the same signal whose normalized frequency lies in the interval minus pi to pi, not including the endpoints. Okay? How do we find that? How do we find that? We find that, like I said, similarly to how we found the principal continuous time alias in continuous time. We call this guy, we call this the principal alias of x of n. And notice it doesn't have to be with respect to anything. Alias here has a different meaning from what it does in continuous time. It's just a different way of spelling x of n. The principle of alias x of n, it takes the form a cos n omega hat prin plus or minus phi. And you'll see where the plus or minus gets decided. As you won't be surprised, I don't think. And the omega hat prin is between minus pi and pi, not including the endpoints. Okay, so how to find it? You draw omega hat space. This is going to feel awfully familiar. Zero's in here someplace. And say here's pi and here's minus pi. Minus pi to pi in omega hat space turns out to be a really happening neighborhood. And we're going to spend most of our time there. But omega 0 hat is going to be out here, say, omega 0 hat. So we're looking at x of n equals a cosine n omega 0 hat plus phi. All right, so how do we find the spelling of that signal, the different way to write that same signal with the lowest possible omega 0 hat bigger than 0? Well, what we do is we take omega 0 hat and we step it down by integer multiples of pi, of 2 pi. So you step, first I'll write the instructions, step omega 0 hat down by integer multiples of 2 pi. Eventually, you will land in at some point in the interval minus pi to pi. And the assumption that the pesky boundary case is not in play means that you're never going to hit pi, you're never going to hit minus pi. There's going to be a unique place in here where you land. So you step this down, you go blump, blump, say blump, like so. So here's where you land in this picture. And you could, depending on where omega 0 hat is, land over here as well. This is just like the computation almost of the continuous time principal alias. All right, so if you land to the right of 0, if you land in the interval 0 up to pi, we call omega hat prin where you land, and the principal alias spelling of x of n is this: x of n equals a cosine n omega hat prin plus v. If you land to the left of 0, as we do in this picture up here, then omega hat prin is minus where you land. And the principal alias spelling of x of n is going to be x of n equals a cosine n omega hat prin minus v. So it comes out the same, like the same kind of drill as we had in continuous time, except instead of stepping down by integer multiples of some fs and getting different signals all the way, we're stepping down by integer multiples of 2 pi, and all the cosines of these frequencies are the same signal, you know, that kind of thing. OK. The book, by the way, uses terminology that when you land to the left of 0, and therefore you have to reverse the sign of the phase to get the principal continuous time, the principal discrete time alias spelling of x of n, they call that a folded alias. You know, I don't want to go there, at least for now, but anyway, that's how you get those. All right. So, question. OK, someone found this discrete time sinusoid under a rock on Leib's slope. They didn't sample it. They didn't sample a continuous time signal to get it. So here's a question. Suppose you're given x of n equals a cosine n omega 0 hat plus phi. I'm not telling you what omega 0 hat is. It's just positive. Omega 0 hat is bigger than 0. Phi is in minus pi. A is bigger than 0. That's all you know about that. Given that, comma, what happens when we put that discrete time signal through the magic box, through the Sinc function interpolator with some interpolation interval Ts? OK. So what happens when we put x of n through an ideal d to c? Remember, there's no background continuous time story to this tale. So there's no background continuous time story here. This x of n is just a thing unto itself. Didn't come from sampling. Some continuous time signal, just found under a rock. So here's the picture. We have x of n. We put it into an ideal d to c with interpolation interval t sub s. T sub s is not part of any background continuous time story here. It's just a number. Y of t is the signal that comes out of that. So what is y of t going to be? What is y of t going to be? Does it depend on Ts? Well, yes, it's going to depend on Ts. Is y of t always going to be a sinusoid? Anyone want to hazard a guess? Critique, you think it is always going to be a sinusoid? Why?
Might not be a pure sinusoid, but it will be a sinusoid.
It might not be a pure sinusoid, but it'll be a sinusoid. What does that mean? What is a sinusoid that's not a pure sinusoid?
I mean, like some of
When I say sinusoid, I kind of mean pure, you know, because I'm a sinusoidal purist. I mean, to me, it's not obvious right off the top of my head. Like, if I put this in here, I'm going to get a continuous time sinusoid out. So to me, it's not even obvious what form y of t takes. Well, it turns out I'll tell you the punchline, and then next Thursday we'll prove it. It's easy. It's just a result of the, sampling theorem. It turns out that what comes out is, actually I won't even write it down. I'll just tell you that. It turns out that what comes out is the continuous time sinusoid you get by first finding the principal alias spelling of x of n, and then doing a simple substitution, 2 pi f0 ts equals omega hat prin. That's what you get. And so we'll do that next time. And so actually, I lied to you on my email last night that you don't have quite enough to do all the problems on the homework that I just posted last night, but you will after next Thursday. You'll be able to do most of them now, but you won't be able to finish them. And I have still some graded homeworks 1 if you want to come by, grab one.